Okay, this is 5.1. Graphs of reciprocal functions. Rather a long lesson, so we're going to try and get through it as best we can. So the goal is to sketch graphs of reciprocal of linear and quadratic functions. So we did look at reciprocal functions a little bit earlier in this course. Remember, they were function notation. They look like this. Okay, we're going to look at them quite a bit closer in chapter 5. And specifically what we're looking at is how we can derive from the original function how to go to the reciprocal function and some of the characteristics of the original function and how they translate onto the reciprocal function. Yes?
So is that the same as inverse? Inverse function?
Yeah, exactly. So reciprocal is the inverse, right. Okay. So here we can see on this graph, and this is the easiest way to learn it. I'm going to zoom in here. I'm going to go over some features, and then we're going to talk about them in length, okay? So this is the best way to to visualize it because it's the simplest function, right? F at x equals x. Okay, we all know what that graph looks like. It's just a straight line passing through y equals x. Okay, that's this graph here. Okay, the reciprocal function to f at x equals x is 1 over x, which is also a parent function. Okay, so this is the graph we're going to be using to kind of establish all of our rules and criterias, and then we're going to go from here and apply them to more complex graphs. Okay, but if we just look at this, first and foremost, we can see a few things that we notice. So when we have an intercept, or when the y value is equal to 0 on the original graph, so f at x equals x, on the reciprocal graph, we have a vertical asymptote. Okay, do you see that? So the original graph, which is here, crosses through x equals, or y equals 0 at x equals 0. So on the reciprocal graph, we have a vertical asymptote at x equals 0. Okay? And this might be a little bit confusing because it is actually so simple that some of the coordinates seem a little bit, they're hard to kind of identify. But as we go, you'll see some things will start to make sense. So as we approach infinity here on the original graph, right, you got to think of x going to infinity. On the reciprocal graph, as x goes to infinity, this value is going to go to 0, right? Everyone understands that? That 1 over x, as x gets larger and larger, this is going to get closer and closer to 0. Does that make sense? So if we have any graph now, any original graph that goes to either infinity or negative infinity, both cases, the reciprocal graph will go to 0. Okay, or it'll approach 0. It'll never get there. So if we have n behaviors that go to infinity on the original graph, whether it looks like this or whether it looks like this, okay, both these n behaviors are going to a y value of infinity. Both these n behaviors are going to a y value of infinity. This n behavior is going to y value of infinity. We're going to have a horizontal asymptote on the reciprocal graph of y equals 0. Does that make sense? Because as these go to infinity, the reciprocal is going to go to 0, or it's going to approach 0. Does that make sense? And it doesn't cross 0 because, remember, this value here, 1 over x, this is getting larger and larger and larger and larger. So this is getting closer and closer and closer to 0. Okay, so any n behavior that goes to infinity will have a horizontal asymptote on the reciprocal graph at y equals 0. Okay? A few other characteristics. And I'm kind of giving you guys a summary of the lesson before we start, but I think it's important because there's quite a bit of things that you need to understand. And we can learn them all just by looking at these two graphs. Another important point, the intersection point, okay, is always at y equals 1 and y equals negative 1. Why? Because the reciprocal of 1 is just 1, right? It's 1 over 1, which is equal to 1. The reciprocal of negative 1 is negative 1 over 1, which is negative 1. So when we go from our original function to our reciprocal function, sorry, I'll zoom out a bit. when we go from our original function to our reciprocal function, when our original function's value is 1, the reciprocal of 1 is still 1. That makes sense? Because 1 over 1 is 1. The reciprocal value of -1 is still -1. Therefore, our intersection point between the original function and the reciprocal function is always going to be the same at the y value 1 and the y value is -1. Okay? On the original function, when y value is 1, on the reciprocal function, when y value is 1, you're going to have the same point. Okay, so on those 2 points, they're always going to intersect. And why? Because the proof is right here. When you take 1, you take the reciprocal, it's still 1. Take the reciprocal of -1, it's still -1. We know 1 is the only number that has that property, right? So that's why you have an intersection point at y equals +1 and y equals -1. Does that make sense? Okay. All right, so that's kind of a summary, and then we're going to kind of prove all of those as we go through this investigate. All right, so let's start. So it says, Owen has noted that some connections between the graph of f at x equals x and its reciprocal 1 over x. By first looking at it, there doesn't look to be anything similar between these two graphs. One is a basic line and one is, these funky curves with all these vertical asymptotes. Our job today is to determine and to show that there are actual real relationships between these two graphs. Okay, both graphs are in the same quadrants for the same x values, so that's a really kind of elementary observation. They happen to be in the same quadrants. Okay, fine. When f at x equals 0, there's a vertical asymptote at g at x. So here's f at x, right here in blue. Actually, let's color that red. Okay, there's our f at x. So when f at x equals 0, which is this point right here, there's a vertical asymptote at g at x. So here's our g at x in gray, and we have this vertical asymptote happening. So we talked about that. The reason for that, okay, f at x is equal to 0. So x is equal to 0 in the function f at x is equal to x. 1 over x is going to be 1 over 0. So that's why 1 over 0, we have a vertical asymptote. Okay, and we all know that. Is there any questions about why 1 over 0 is a vertical asymptote? Because that value is undefined, right? So on the graph, it's undefined. That means when it's undefined, no values touch it. Okay? So that's why when f at x is 0, g at x is a vertical asymptote. F at x is always increasing and g at x is always decreasing. So remember, when we're deciding whether a function is increasing or decreasing, we have to read from the left to the right. So if I read from the left to the right for this f at x, the red graph, it's always moving up. If I read from left to the right, although it's not as clear for this g at x graph, you can see if I read from the left to the right, it's going down, 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 going down. I start up over here, again, it's going down. Any questions there? And so let's talk about why that makes sense. If my f at x value, so here's my original function here, f at x equals x. If my x value is increasing, going up and up and up and up, well, my g at x has to be going down because as x gets bigger, this value gets smaller. Does that make sense? And the opposite happens as f at x goes smaller, this value gets bigger. Okay, because it's reciprocal. 1 divided by a smaller and smaller number means it's going to get larger. Any questions up to there? This can get confusing pretty quick if you're not on board so far. All right, let's start. How are the graphs of the function and its reciprocal function related? Explain why the graphs of f at x equals x and g at x equals 1 over x are in the same quadrants over the same intervals. Does this relationship hold for m at x equals negative x and n at x equals negative 1 over x? Does this relationship hold for any function of its reciprocal function? Explain. So if we try this, so there's m at x equals negative x And now if we flip this function, we're going to have this is n at x equals negative 1 over x. So what we notice then is, yes, in fact, they do stay in the same quadrants. Okay, which makes sense because if you put a negative sign in front of the x here, that negative sign is going to go with the x down here in the reciprocal function. Okay, so does this relationship hold true for any function and its reciprocal function? Yes. It does. Negative sign transfers to reciprocal function. Any question there? Okay, just because we're taking the reciprocal doesn't mean we change the sign. If we do change the sign, we have to change the sign on the reciprocal. All right? So that means any positive x values for y values for the original function are going to be positive y values for the reciprocal function. Okay, and likewise vice versa for negative values. Okay, B. What graphical characteristics in the reciprocal function do the zeros of the original function correspond to? So I've gone over this. So what do you guys think? Can anyone answer this one? The zeros of the original function. What graphical representation in the reciprocal function occurs? Yeah, Lyndon? Sorry? Say that again?
For 1.
For 1?
So I think it's the zero which crossword is intercept.
Okay, so hold on. Let me just help you out here. So the 0 for the original function is where? Is what here?
0.
Yeah, good. So the 0 for the original function is x equals 0. So what's happening at x equals 0 on the reciprocal function?
It's still an asymptote.
Yes, it's a vertical asymptote. So let's summarize B here. Okay, so zeros on the original function So zeros on the original function result in a vertical asymptote on the reciprocal function. Okay, and we should see that. We should see that here, right? As x goes to 0, this goes to 1 over 0. So this is undefined, which is equal to my vertical asymptote, and this is my zeros on graph.
So is it also referring to f of x equals x, the line?
Yeah, it's the 0 out of that line, right? It's the 0. When does the original graph cross the x-axis? Crosses at 0. So on the reciprocal function, you're going to have a vertical asymptote at 0. Okay? Any questions about that one? All right. C. Explain why the reciprocal function g at x equals 1 over x is decreasing when x is increasing. Yeah.
So as x is increasing, as you see when a greater number is, when 1 is being divided by a greater number, it starts to decrease. So
Right. Yeah. So as this number goes up, this number is going to go down, right? We know that from basic math, right? As the denominator goes up with a constant numerator, the value is going to go down of that function, right? So wherever I have x increasing, my reciprocal function is decreasing, okay? So let's look at the graph and see if that's happening. If we look at our original graph, x is increasing throughout, everywhere. And in our reciprocal graph, x is decreasing throughout, everywhere. So if you go to graph a reciprocal function, and I look at the original function, and I see the original function is increasing over a certain range of x's, and I look at your reciprocal function, it needs to be decreasing over that same range. Okay? This is going to make a little bit more sense as we go through a little bit more complex examples. Because this is always increasing, it might be a little too simplified, but you'll see. Okay? Does it apply to this graph as well? That's the question. So x is always decreasing on this graph. X is always increasing on the reciprocal. Okay, remember, always reading from left to right. Any questions there? Okay, D. What are the y-coordinates of the points where f at x and g at x intersect? Will the points of intersection for any function and its reciprocal always have the same y-coordinates? Explain. Okay, so this is where we talked about this scenario. Okay, so this is D. Okay, when we take the reciprocal of the y value 1, it's still going to be 1. When we take the reciprocal of -1, it's still going to be -1. Okay, so what are the y-coordinates of the points where they intersect? They're 1 and -1 is where they intersect. Okay, will the points of intersection for any function and its reciprocal function always have the same y-coordinates? Yes. Okay, and the explanation is right here. Okay, they have the same y-coordinates. Why? Because when you take the reciprocal of 1 and -1, it's the same value. Any questions on that one? All right. Explain why the graph of g at x has a horizontal asymptote. What is the equation of this asymptote? Okay, so first of all, g at x, again, is this graph over here. The equation of this horizontal asymptote, Kevin, is what?
The horizontal asymptote?
Yeah, on this graph.
Y equals 0?
Yeah, so the horizontal asymptote is y equals 0. And why do you think it has a horizontal asymptote? Can you explain why? I explained it earlier, so something to do with the end behaviors.
Oh, as x reaches infinity,
Yeah.
the reciprocal function, it approaches 0 also.
Right, yeah, because it's 1 over infinity, right,
It's
is close to 0. 1 over a very large number, or even if it's a negative number, a very small number, is still going to be 0. So as it approaches infinity or negative infinity, you're going to have a horizontal asymptote at 0. Okay? So explain why the graph, what is the equation of this asymptote? Y equals 0. Will all reciprocal functions have the same horizontal asymptote? Explain. No, only if values approach infinity will you have a horizontal asymptote at y equals 0. Okay, not all reciprocal functions will have an asymptote at y equals 0, only the ones that the original function approaches infinity or negative infinity. Okay? Which is actually the case for all polynomial functions, right? So for polynomial functions, yeah, that will be the case, right? Because all the exponents are positive whole numbers. Okay, so we will have these conditions. Okay, on graph paper, draw the graph of x squared minus 4. In a table like the one below, note the characteristics of the graph of p at x and use this information to help you determine the characteristics of the reciprocal graph. So we know, very simple graph again, negative 4, 1, 2, 3, 4. We have our vertex down here. We have a graph that looks like this. Okay, we can find out where these zeros are by plugging in 0 for y and solving. So we'd have plus or minus 2. So this is 2. This is negative 2. Okay, you guys understand that, right? 0 is equal to x squared minus 4. X squared is equal to 4. X is equal to plus or minus 2. Okay, so there's our graph. Could have also done the step value, gone over 1, over 1, up 3, and got there as well. Step pattern. Okay, so there's our graph. So, zeros and or vertical asymptotes. Any vertical asymptotes here? Joseph? Sorry?
Vertical?
Yeah, vertical asymptotes. Horizontal asymptotes. Yeah, what?
Horizontal.
Where?
No, it's just
There's no asymptotes, right? What are the zeros?
2, negative
Yeah, so plus 2, negative 2, right? Intervals on which the graph is above the x-axis. Nailed.
negative 2 and 2.
The intervals between negative 2 and 2 is above the x-axis? No.
Oh, 2 and infinity and negative infinity and negative 2.
And?
And 2 and infinity.
Yeah. So going from negative infinity to negative 2, so all of these values, and then going from 2 to infinity, all of these values. Intervals on which the graph is below the x-axis. So I could write from negative 2 to 2, or if you prefer, x is greater than negative 2, x is less than 2. However you prefer to write it. This is interval notation. Okay, and this is standard notation. Intervals on which the function is increasing. Jesse.
2 to infinity, and from negative 2 to negative infinity.
From 2 to infinity,
Oh,
and from negative 2 to negative infinity. Okay.
no, sorry. It's from 0 to infinity and 0 to negative infinity.
Very good. Sorry, what was the other one you said?
0 to negative infinity. That's what increasing.
No, it's not increasing. Remember, you got to read from left to right.
Oh, yeah, sorry.
So there's just one, right?
Yeah.
Okay. You guys all understand that? From here down to here, it's decreasing. It only starts from 0 that it starts increasing. Okay? And then function where it's decreasing from, Totone? The interval in which the function is decreasing. So there's our function.
Negative infinity to 0?
Yep. Points where y value is 1. So here's our y equals 1, right? Here's our y equals 1. So we have 2 points. How can we figure out those values? David.
Plug in the equation.
Right? So we're going to plug in y equals 1 up here. 1 is equal to x squared minus 4. X squared is equal to 5. X is equal to plus or minus the square root of 5. points where the y value is -1. -1 equals x squared minus 4. X squared is equal to 3. What is square root of 5? Just so I have a decimal value as well. Sorry? Thanks. And square root of 3? 1.7? 1.7?
73.
Okay. Any questions up to here? Okay, this is all the easy part, right? This is all just looking at this graph. Everything we should know. There's nothing that we haven't done here that hasn't been from review. Okay? Now, today's lesson, the reciprocal function. Everything we've learned today. So zeros and or vertical asymptotes. So here's our function. 1 over x squared minus 4. Are there any zeros? Okay, tell me good. You're right, Marco, but why?
Because whenever x is equal to y equals 0, it doesn't exist.
Right, exactly. So if we were to try and plug in 0 here, okay, so here's our equation right here. Q equals, if I said 0 is equal to 1 over x squared minus 4, okay, this would give me 0 equals 1. Okay, so it doesn't exist. Right? Okay, so that's undefined. So there's no zeros. So what does that mean practically on the graph if there's no zeros? Nicholas?
There's an asymptote.
Okay, you could say that, but in other words, it just doesn't cross 0. Right? It doesn't touch the x-axis. Okay? But you're right, there is a vertical asymptote somewhere. Where would that be?
2.
Philip.
Pardon?
Vertical asymptote. This function, where would it be?
2 and then
1. 4 and negative 4.
Sorry? 2 and negative 2. Okay, there's two ways Philip could have figured that out. Okay, one way could have been that he was listening earlier in this lesson and he knew at the zeros of the old function there was vertical asymptotes on the new function. Why? Because we talked about, well, when f at x is equal to x and x is equal to 0, then we have a 0 happening on the original function, and then when the inverse function was 1 over x, we had 1 over 0, so we knew that was an asymptote. Or he could have used previous knowledge and just figured out, well, if I plug in 2 or negative 2 for x here, then I'm going to get 1 over 0. So I can figure out your vertical asymptotes that way. Okay? The point of today's lesson is that you want to use this method. You want to realize that at the zeros on the original function, you have asymptotes on the graph. Because it might not always be this easy of an equation, but you might have a graph for the original function. So if you have a graph for the original function, you find out where those zeros are here and here, and you know on your new graph, you're going to have vertical asymptotes going through those points. So whatever new graph we draw here in red, we cannot touch those negative 2 and 2. Any questions up to there? Okay. Intervals on which the graph is above the x-axis. All the values of the function are positive. So what do we learn about this? What are the intervals where we have positive values? Let's try Kobe. So we talked about this at the beginning. We talked about how when it's positive on the original function, it's still positive on the new function, right? So here's our example again. When we're positive on our original function, we're positive on our new function, right? We're above the x-axis and below. And even when we switch them, same thing. Positive, we're both positive, okay? So having said that then, what would our intervals be? They're going to be the same, right? Exactly. And that's again because that negative sign, if that goes negative, it's going to follow. It's going to stay negative. Okay, intervals on which the graph is below the x-axis. So negative. Ramon?
Oh, it would be the same thing.
Right, it's the same. Okay, so it's below here between these two values. It's going to be below there on our reciprocal graph. Intervals on which the function is increasing. Kevin?
Negative infinity to 0.
Okay, so it's the opposite now because we talked about this. Remember looking at the original graph? If this is increasing, this is decreasing. If this is decreasing, this is increasing. Okay, so this is going to be, function is decreasing, it's going to be the opposite. So these switch. And finally, points where y value is equal to 1. Okay, we can do this by subbing in 1 for y here. Okay, we sub in 1 for y up here in the reciprocal function.
So could you move it?
Yeah. We're going to get plus or minus square root of 5. And here we're going to get plus or minus the square root of 3. Okay, we get the same values. Sub in negative 1, you'll get the same value. And that's because 1 over 1 is still 1, and 1 over negative 1, or negative 1 over 1 is still negative 1. Okay, so these values are the same. So, if I want to draw my new graph now, here's f at x. Okay, now I want to draw in red my reciprocal. So I know a few things. So one thing I know is that this point at y equals 1 is a point on my reciprocal. So I can actually color it red. And y equals negative 1, which is down here. This point is also okay, and this should have been okay. Now let's try and draw this. What do we have? So we have a vertical asymptote at y equals, sorry, x equals 2 and x equals negative 2. So that red I cannot cross. Okay. Next I know my values are positive, so I have to be in this area. I have to be positive here, and then I have to be down here on my negative. Okay? So guys, pay attention here, because this is a big part of the lesson, right? How to draw, once we have all this information, how to draw the new graph. Okay, so I'm trying to think it out, going through it slowly here, so please pay attention. So I've drawn my vertical asymptotes. I've drawn those points at root 5 and root 3 where my values are the same. So I know because these values here are decreasing on my original function. Okay, here's my original function in blue. The values are decreasing. I know my values have to increase, and I also know there's a horizontal asymptote at y equals 0. Here's my y equals 0, and I have to increase. So there's only one way I can draw this. Okay, I'm increasing, I cross through that point, and I continue to increase, and I don't hit my vertical asymptote, and I don't hit my horizontal asymptote. So I didn't draw this because I knew the graph looked like this. I drew this because I knew it was increasing, I knew I had to be in the positive quadrant, and I knew I had to hit this point, and I couldn't hit this, and I couldn't hit this. There's only one way to draw that. That's very important that you guys understand that. Okay, next. I'm going to draw now down here. I'm still decreasing, so I have to increase as I come up to this point here. I have to increase, but then I have to start decreasing where this increases. And I can't hit this value. So I have to draw okay, and I appreciate the confusion initially with those laughs, but let's just talk about it, okay? I have to cross this point here. Okay? Part of the issue with this is my graph has not a high enough resolution, okay? So it's hard to see. I'm trying to cross through this value of y is negative. Sorry, where my y value is -1, I'm trying to cross through negative 1.73 on the x. So it's very close to my vertical asymptote. So that's why this drawing doesn't look great. Okay? But it's important to note that I'm decreasing here, so I'm increasing. As soon as I get to 0, I start increasing the original function, so I start decreasing. I can't touch the horizontal asymptote. I start decreasing. Again, I have to go through 1.73.
Sorry for interruption.
Right there.
Mitchell Rosinsky, please report to room 413. Mitchell Rosinsky, report to room 413.
And I'm decreasing. Let's look at a better. And then finally, I'm increasing here, so I have to be decreasing. Can't touch that. Need to go through that point. And my graph looks like that. Okay, here's a better version of it. Okay, what made this particularly tricky is, again, this value right here. So if I were to point it out, my y is equal to -1, and my x is equal to 1.73, and then I have a vertical asymptote at x equals 2. Okay? So that's what made this whole scenario difficult, this point here. Okay, likewise, when y was +1, I had to cross through the x value of 1.73, but also still kind of level out at y equals 2. Okay, any questions?
So that was when they're crossing, right? The points.
Yes.
Yeah, so what the
Sorry?
Why is that graph?
Why what?
The negative x squared graph.
I can't hear you.
You know that graph in the middle? Between right there, yeah.
Yeah, this?
Why is that there?
Why is this here?
It's the negative.
Because when you have negative values on the original function, you have negative x values on the reciprocal function. And when you have decreasing values on the original functions, you have to have increasing values on the negative reciprocal function. So it still has to be here. And then you can't touch this value of the horizontal asymptote at y equals 0. Okay? Let's look at a few others and see if it'll start to make a little more sense. Okay? Let's look at here. Okay, we're going to look at the next one here. B. Okay, let's look at this one here. X plus 2 and 1 over x plus 2. Okay? So here's our graph. X plus 2, we all know, is just a straight line. Okay? We've raised up the y-intercept to 2, so we have this line here. Here's our y equals x plus 2. Okay? And then here's our reciprocal function. One over x plus 2. Okay? So you have to be able to go from this straight line to this function. Okay, the reciprocal function. So let's see if we can do that just by looking at the straight line. So we know the straight line crosses through x equals negative 2. That's the only 0. Okay, so on my reciprocal function, I draw a vertical asymptote here. All right, this is part 2 of 5.1. We've been talking about graphs of reciprocal functions. Went into the end of the last period. Just as a quick review to get us back up to speed. One of the things that I overheard, I heard somebody said, it's as long as I can remember all the rules, okay, it should be easy. And it's not really what I wanted to hear. That's kind of not what I want. I want you guys to kind of remember conceptually what's happening. If you have a better understanding of these two graphs, the y equals x and y equals 1 over x, then you don't have to really remember any rules. You should know by just kind of going back to this idea in these graphs. Okay? So what I mean by that is if your x value is 0 on the y equals x graph, then your reciprocal value is going to be 1 over 0. Right? So you're going to have an unknown or a vertical asymptote at that point. Okay? If you approach infinity on the original function, then you're approaching 1 over infinity on the reciprocal function. Right? You're just taking the reciprocal. So all of the kind of behaviors on the original function, you just put it 1 over that behavior, or 1 over that x value, and you should get the behavior on the reciprocal function. Okay? If it's increasing on the original function, then it's going to be 1 over an increasing value, so it's going to be decreasing on the reciprocal function. Okay? So you should be able to, like, not just memorize all these kind of quote-unquote rules, but rather just go back to this idea of x versus 1 over x. So what's happening on this graph, and then put it 1 over that. And that'll be what's happening on the reciprocal function. Okay? So another thing we haven't mentioned yet is the y-intercept. Okay, if the y-intercept, let's say for this value, this is a bad example because it's 0. Let's look at this, okay? This graph here. Sorry? Okay, so this graph, our y-intercept is 2 for our original function. Who can tell me what the y-intercept is going to be for the reciprocal function? You don't need to know x plus 2. You don't need to know 1 over x plus 2. All you need to know is that the original function y value is equal to 2. The reciprocal, so I'm going to say y-intercept. The reciprocal at y-intercept is going to be equal to what? Now you can see it on the graph if you look carefully, but you should know intuitively. What's it going to be, Kevin?
1 over 2?
Yeah, 1 over 2. Because that's all it is. It's the reciprocal function. It's a reciprocal value. So whatever y value we have, the equal value for that x value on the reciprocal function is going to be 1 over that value. Because it's an exact reciprocal. So I don't have to do any math. I don't have to plug it into the equation. I just know, well, if the y-intercept is 2, the y-intercept of the reciprocal function is 1 over 2. Okay, and we see that happening here. Even though we have this really kind of funky graph going on, we can see that it crosses through right at 1/2. Okay? The original function crosses at 2. The reciprocal function crosses at 1/2. Let's look at another one. Okay, here. Here's our original function. It's a straight line. We can see the y-intercept is -3. So our y-intercept for the reciprocal function is going to be what? It's going to be -1/3. Okay? So y-intercept of original function say is equal to -3. The reciprocal is equal to -1/3. Let's see if we can do it on another graph. What about any y value? Any y value. What is the corresponding y value going to be on the reciprocal function? It's not just y-intercept, right? If we look at an equation like this, and we see that this y value, say here, is -4. We see right here, this is +1, -4. Okay? That's a point on our original function. Everybody can see that, right? There's no mystery there. The point for the same x value, so +1 here, the x value, +1, on the reciprocal function, the y value is going to be -1/4. Does that make sense? So now, not only have we established all of these rules that we can go to, but we can actually check individual points quite easily. Joseph?
So, sir, if that was 2 and -4, would it be 1/2 and -1/4, or would 1 stay? Sorry, the 2 stay.
The x value stays the same. Okay? Okay, so let's see, where did we leave off? We finished off with an example. We had a table of values. Sorry, I gotta stop there. All right, part 3 of 5.1. So we were talking about y values on the original function. What are they? What would they be on the reciprocal function? It's going to be 1 over that same y value. Don't have to do all the calculations over again. If you already have the y value calculated for the original function, you can just flip it and you'll get the y value for the reciprocal function. Okay, so let's do one last example here. So we have the function f at x equals x minus 2, x plus 3. Okay, and then we have implications for the reciprocal of that function. Alright, so f at x -1 is 1 over x minus 2, x plus 3. Okay, so first and foremost, the zeros, we already have it set up in factored form, so we can identify the zeros right away. They're +2 and -3. What happens at those zeros on the reciprocal function? Daniel. Zeros on the original function, reciprocal function.
The same zeros.
No. Pay attention. Marco? Yeah, vertical asymptotes. Think about it again. Let's think logically about it. When x equals 0, okay, we have a 0. Or sorry, when y equals 0. Right? That's a 0. So our x value on the original function is x value is equal to -3 and 2. On our reciprocal function, y is going to be 1 over 0. Okay? And this gives you a vertical asymptote. And this is probably off screen. No, it's on. Good. Okay. So we have vertical asymptotes at -3 and 2. Next, we have intervals on which the graph is above the x-axis and below the x-axis. Remember, these are the same, right? The sign doesn't change just because we take the reciprocal. The sign stays the same. So where it was positive, it's going to stay positive. All right, so these are the same. These are equal. Okay, same thing for the intervals where it's negative. So anywhere going to a graph, anywhere the original function, which this is the original function in this parabola, wherever it's above the x-axis, that's where the reciprocal function has to be, above the x-axis. Okay, when you go to draw these, there's going to be so many indications whether you made a mistake or not. That's a big one. I can easily just look at a graph and see, make sure they're all on the same side of the x-axis to make sure that you've drawn it correctly. Joseph? Okay. All right, so those are the same, those are the same. Intervals on which the function is increasing. Now remember, these are going to be opposite. Okay? And that's because of that whole x versus 1 over x relationship. As x increases, 1 over x decreases. Okay, so that's why the intervals on which it's increasing, here it's going up. So the reciprocal function, it's going down. Up, down, down, up. Okay? All right, so those are opposite, and those are our intervals from the graph. Finally, points where the value of y is 1. To get these values now, you need to sub in the value of y equals 1 into the original function, and then solve for x. Okay, that's where these values come from. They sub into here, y is equal to 1. Okay, you expand, simplify, and then solve. You'd probably have to factor again and solve for x. Any questions with these values, where they come from? And remember, these values are going to be the same on the reciprocal function. Why is that the case? Nicholas, why do you think that the points where the y value is 1 is the same on the reciprocal as it is on the original?
Because if you're still putting it 1 to the equation, everything just follows.
No. International rule of math you learned in grade 3, I think. Anything divided by 1 is 1. Right, good. Okay. Likewise, when we divide by -1, we're going to get that same -1 value. That the signs will change, and these become the same. Okay, any questions? All right. We're going to move on to the examples finally. I have them in color. Let's put them in color. Okay, still quite a long lesson to go. 4 pages. All right. Much nicer. Okay, example 1. Connecting the characteristics of a linear function to the corresponding reciprocal function. All right, example 1. Connecting the characteristics of a linear function to its corresponding reciprocal function. That's what we've been talking about the whole time. Given the function 2 minus x, so they've tried to fool you guys here and just write this out of order. We know this as negative x plus 2. Okay. So we know it has a slope of -1 and it has a y-intercept of 2. Determine the domain and range, intercepts, positive, negative intervals, and increasing, decreasing intervals. Okay, so the first step would be, to make this easier for yourself, would be to make a graph. Okay, this is one of the few scenarios where graphs actually do help quite a bit because they can allow you to visualize the function and then answer all these questions quite easily. All right, so the first one is domain and range. Here's our graph of y equals 2 minus x, or minus x plus 2. So it's just a straight line with a slope of -1 going down. Our domain and range, easy enough. Our domain is xer because it covers all the x values, and range is yer. Our positive and negative intervals. So in this case, we only have a negative interval. It's always decreasing. Okay, reading from left to right. That's how we determine that. It's always decreasing. Our positive and negative intervals is actually the values of y. They're positive when they are greater, when x is less than 2, and they're negative when x is greater than 2. Okay? And so we can also display that as positive, negative infinity to 2, and negative when 2 to positive infinity. And finally, the decreasing intervals, it's always decreasing. So from negative infinity to infinity. Any questions with this part? That's very, very simple, straightforward. It's just analyzing the original function. Next, we want to use our answers to sketch a graph of the reciprocal function. All right, so how do we do this? So the first step for reciprocal functions, I'm not sure if we covered this or not, but in our reciprocal functions, the domain of the original function becomes the range of your reciprocal function, with the exception of the asymptotes. Okay? So we know we have an x-intercept here at x equals 2. So we have a vertical asymptote. Sorry, thanks. We have a vertical asymptote at x equals 2. Okay? That comes directly from our 0. Okay? If we have a vertical asymptote at x equals 2, our domain is going to be xer, where x cannot equal 2. And our range is going to be yer. Because we approach negative infinity and positive infinity in both directions, we know we're going to have a horizontal asymptote at 0. Okay? Remember that? As x values go closer and closer to infinity, the reciprocal values go closer and closer to 0. So y cannot equal 0. Any questions about that so far? Domain and range. Okay. Next, our y-intercept is going to be what? Just went over this. Nicholas, what's the y-intercept going to be of our reciprocal function?
1 over y-intercept?
Yeah.
It's going to be 1 over 2.
Yeah. Thanks, Marco.
I didn't listen to Mark.
Y-intercept is 1 over 2. That's because our y-intercept in our original function is positive 2. So we take the reciprocal. Okay? Next, we want to list our vertical asymptote. We've already done that. Positive and negative intervals. So our positive and negative intervals. Okay, they're going to be the same, right? Because we've decided that the sign doesn't change when we go to the the reciprocal function. So that's going to be that and negative and finally increasing, decreasing. Increasing is the opposite, so it's going to be negative infinity to infinity. Does since the other function was decreasing the whole time. And finally, we're going to use all of this information to sketch the graph. Okay. So my positive, I'll put the other function on here for reference. Okay. So this is the part where you guys want to pay attention, right? Because this is kind of the difficult part. This is where we actually have to draw it. So from my graph is always increasing. I know my y-intercept is here. Okay, I know I have a horizontal asymptote at y equals 0. So I'm increasing. I cannot touch here, so this is going to be going down. I'm going left to right. I'm coming up through here. And I have a vertical asymptote at x equals 2. Okay? So it's very important that you set your graph up correctly. Okay? You put in your vertical asymptote, you put in your horizontal asymptote, you put in your y-intercept, and then you use the positive and negative intervals as well as the increasing and decreasing information to draw. Okay? So I'm increasing, I have to go through 1/2, I have to keep increasing, and I cannot touch that line. Okay? There's no other way I could draw this based on the information I have. Next, I'm still increasing, but I have a vertical asymptote here, so I have to come up like this. Like that. Okay? What's this point and this point? What should they be? Marco?
When y is equal to 1.
Right, this is when y is equal to 1, and this is y equals -1. Okay? So that's another hint, right? If you have your axis on here, you know that they have to cross through that point and that point. Any questions? So, you know, as much as you start with a blank piece of paper to begin with, after you put in all of these rules and all these constrictions, there's really only one way to draw it. And I can tell you from experience, it just takes a lot of practice and you'll draw these things pretty quickly. All right, let's go to the second example. There's the graph that I just drew. Don't forget to label it as well. And there's that last part. The graph of g at x intersects the graph of g at x at 1, 1, and 3, -1. How did we get this value here? Okay, how do we get that value? Joseph.
Just plug in 1 and -1 into the original equation.
Yeah, you got it. Exactly. Good. You plug it in for y though, right? We're so used to plugging in for x, but you plug in this for y. Which one are you going to use, Joseph? You're going to plug it in here, or are you going to plug it in here?
G at x?
Yeah, they're both g at x, but...
The second one?
Yeah, why?
Because it's the original.
Okay, so what? I could plug it in here. I'm going to get the same answer. Why would I plug it in here?
It's easy.
Yeah, it's easier. You're going to get the same answer, okay? All right. Connecting the characteristics of a quadratic function to its corresponding reciprocal function. Given the function 9 minus x squared. So again, this is just a parabola opening down that's vertically translated 9 units up, right? Everybody can see that, right? So the graph, you know, the graph looks like this, where this is 0, 9. Okay? Determine the domain and range, intercepts, positive, negative intervals, and increasing, decreasing intervals. So, the domain of our original function, this is easy, xer. The range has to be less than and equal to 9. See, people are looking bored, so I'm going to go a bit quicker. Okay, the next one we want to figure out what our x-intercepts are. Okay, on the original function, remember these become our vertical asymptotes. So we factor the equation, we move it over to one side, we factor, and we get plus or minus 3. So there's our x-intercepts. These become vertical asymptotes on our reciprocal function. F at x is positive when we go from negative 3 to positive 3. That's on the graph. And it's negative when we're negative infinity to negative 3 and 3 to infinity. So negative over here and positive here. Increasing, we're increasing from negative infinity to 0. We're decreasing from 0 to positive infinity. Okay? The reciprocal function now. The vertical asymptotes, as we mentioned, are at negative 3 and 3. The domain is, again, XER, with the exception of plus or minus 3. The horizontal asymptote is y equals 0. That's because these approach infinity. Okay? That's why we have a horizontal asymptote at y equals 0. The y-intercept is 1 over 9. Why? Because the original function, the y-intercept is 9. So the y-intercept for the reciprocal function is 1 over 9. And finally, there's a local minimum value at 0, 1 over 9. Okay, when the original function has a local maximum point, the reciprocal function has a corresponding local minimum point. So here's a new piece of information that we've learned. Wherever there's a max, there's going to be a minimum. And the reason for that is because it changes direction from increasing to decreasing. So on the reciprocal function, we have to change direction the opposite way, right? If we're always increasing on the original function, we're decreasing on the reciprocal function. If those relationships change, then you must change them on the reciprocal function. So where there's a local maximum, there's going to be a local minimum. Where there's a local minimum, there's going to be a local maximum. Okay? And we say local just because it's possible that these end behaviors can go past them. Okay? So they're not actually technically the complete maximum. In this case, it is, but not always. Okay? And not for our reciprocal function. Any questions with that? All right, almost done. So the reciprocal function. We now know we have vertical asymptotes at positive 3 and negative 3. We know our intersection points here occur at y equals 1. Yep, sorry. Y equals 1 and y equals negative 1. We know we're increasing here, so our reciprocal function, we need to always be decreasing. We know we have a local maximum here. We need to have a local minimum here. We know the y-intercept is 9. It's going to be 1 over 9. Okay? And then we know that we're decreasing here, we're increasing here, and we have a vertical asymptote at x equals 3 here. Okay, so we have to avoid that. And a horizontal asymptote at y equals 0 because our end behaviors approach infinity. Any questions? All right, in summary, you can use characteristics of the graph of a linear or quadratic function to graph the related reciprocal function. All the y-coordinates of the reciprocal function are the reciprocals of the y-coordinates of the original function. That's what I talked about today. So if you have a y value is equal to 2, for instance, the reciprocal is going to be y is equal to 1/2 for the same x value. Don't have to plug it all in to figure that out. The graph of a reciprocal function will always have y equals 0 as a horizontal asymptote if the original function is linear or quadratic, and that the reason for that is because the ends approach infinity. So you got to think of 1 over infinity. 1 over 0 is going to be. Just going to X that. Reciprocal function has the same positive and negative intervals of the original function. We know that because the sign doesn't change. Last page. Intervals of increase on the original function are intervals of decrease on the reciprocal function. We've gone over that. If the range of the original function includes 1 and or negative 1, the reciprocal will intersect the original function at a point where the y-coordinate is 1 or negative 1. It's important that the range must include. Obviously, if the range doesn't include it, it never hits. If the original function has a local minimum, the reciprocal function has a local maximum. We just talked about that. Here's 2 great examples. Very basic, but they tell you a lot of information. Both functions are negative. They just go over the exact same stuff we've talked about. Any questions?